Alright, here's the big cheese, theorem 4.18, Cauchy's theorem. And so we've got a G, a region, F is holomorphic, and we've got these two paths that are homotopic, G homotopic, so in G. Okay, so it says if you've got that, then, and you want to integrate F over gamma 0, you could instead just integrate over gamma 1 or vice versa. Okay, so let's see. So, we've got Cauchy's theorem here. F is holomorphic in G, and we've got the homotopy gamma 0 to gamma 1. And then the theorem says, oh yeah, this is equal to that. And that's amazing, really, because so it's not even really saying exactly path independent, because these are closed loops and we're not trying to get to the same point, right? So you could have typically one would probably be inside the other. To get the 0, 1, yeah, you have to have one inside the other. And but again, you could have gamma 0 just be a circle, and gamma 1 be a triangle, and you say, I don't know how to do this triangle. Oh, but that circle would be easy. There you go. You can do it that way, and that's the whole point. And then they do an example, and they take gamma to equal I think they said a square around 0 there. Let's go back and take a look. Let's see. So gamma is the square in figure 4.1, oriented counterclockwise, and so we're doing a square, and they say, okay, I want to do this integral of gamma of 1 over z dz, but in this region, if we call our region say the complex plane without 0 in it, then F here, 1 over z, is holomorphic. Okay, so if we take that, right, I can take the derivative of 1 over z everywhere, and then well, yeah, that may be hard, but they point out that, and I think they said this is one of the exercises, I haven't looked at them all yet, but they point out that if you let say gamma 1 equal e to the I theta from 0 less than or equal to theta less than or equal to 2 pi, that we can show integral from gamma 1 of 1 over z dz is equal to 2 pi I. Well, so if I've got that result already, then given this square, so we'll draw that square again down here, that went clear out to 3, so there's the unit circle in it, and we already know they're G homotopic, and so I don't I don't have to do this one up here. I can just rely on an answer I already have. So that says, oh, gamma of 1 over z dz is equal to 2 pi I. And so, you know, there's our gamma. And so I got that simple because of a previous result. So that's very, very powerful to do that. So let's see. Okay, so they went over that, and then they do this big long proof. We aren't going to worry about the proof. There they mention the contractible to 0, and if that's the case, then so we had Cauchy's theorem up here that these two things are equal. Well, if gamma is g contractible to 0, then what we know is that the integral over gamma of f is going to be 0. Okay, because you know, it is that same homotopy, and if I am trying to integrate just over the point, I get 0, and so they should be equal. And then of course, you know, they'll later again you could use any point actually and work with it that way. Okay, so another corollary. So this was corollary, I think, 420. Yeah. So corollary 420. Okay, this is 420. But then, you know, 422. Well, it says that you know, if f is entire, okay, so it's differentiable everywhere, then any path of integration that you use, you're going to get 0. Okay, and again, that comes down to I don't know that they really gave a proof of that, but the point is it's you know, its derivative is there at any point, and we can take the original corollary up here and move it to any point simply by doing a variable transform. So, you know, for instance, if I'm around the point 2, 2 with, say, a circle of radius 1, so this would be you know, something like cosine theta and then plus 2 and then sine theta. Oh, well, don't want to use theta, we want to go from 0 to 1. So cosine of 2 pi t and then plus 2 and then sine 2 pi t and then plus 2. Right, so we have that this curve is definitely g homotopic to 2, 2. Well, but now just subtract 2 from everything. Right, and all you've done is taken this whole problem, you know, and moved it, oops, wrong direction, I guess 0, 0 would be over here, you know, and moved it over here. So you just subtracted 2 from every single one of these points, and well, actually 2 plus 2i we subtracted from every one of these points, and and we could do the same with the f. You know, instead of f of z, we would look at f of z minus 2 plus 2i, like that. So we can just transfer everything back here to 0, and so it doesn't matter. You don't have to have your gamma around 0. You're just going to get 0 if f is entire. And even if it's just entire in a subset, in the sense that it's differentiable everywhere in the subset. Okay, so we've got those results. And I think I'll stop there with this video, and then we'll look at their example 4.23. Okay. Oh, I don't think I switched back. So let me go back. Sorry about that. I don't think I ever switched back here. I started drawing. Yeah, I know, I'm a loser. Okay, so I said, you know, here's a circle 2, 2. There's our parameterized path, unit circle around it. But then, you know, all we have to do is subtract, you know, from gamma of t. Well, call it gamma 0. Gamma 0 of t will just be gamma of t minus, actually no, you don't want that inside, do you? Gamma of t minus 2 minus 2i. And that will take all of these points back here. It will make you think of 2, 2 is back here, and then my new f of z, so I could call that f0 of z, would be the old f of z minus the 2 plus 2i. And that would, so when if before you would want z equals 0, well, to get z equals 0 now would be at the point 2, 2 here. And, well, z, the argument in here would be 0. And so I'm sorry I didn't cut back to this. Great explanation, couldn't see it, but yeah, there you go. So anyway, so that's what's going on, is that we've got these nice Cauchy theorem results, you know, the corollaries that go with it, that we can certainly come up with answers to some of these integrals very quickly and easily, because we don't have to go by the rules that are originally set. We can use Cauchy's theorem to maybe make up our own rules. So now I'll go ahead and stop this.